In this topic, we took a look at instrument system alarms and how switches may be used to activate alarms or backup systems or to act as interlocks. Finally, we saw how a controller can be identified, and we examined some of the steps necessary to switch a controller from one mode of operation to another. Now let's try some practice questions. Alarms can be visible, they can be audible, like this siren, or they can be both visible and audible. Alarms are usually activated by electrical switches, which are operated by sensing devices connected to the process. The controller sends a corrective signal to the final control element. In this case, the final control element is a flow control valve. This controller can be switched to manual operation at any time. However, for a smooth transfer back to auto from manual, the value of the process variable and the value of set point should be the same. Otherwise, rapid shifts in control action called bumps can occur. Bumps can adversely affect process operations, and they can sometimes damage equipment. To avoid bumps, the values of the process variable and set point should be equalized before a switch is made from manual to auto. Valves regulate the flow of gases and liquids in process systems. A valve that is operated automatically to throttle flow is usually referred to as a control valve. The control mechanism in a control valve is the valve's disc. The disc works basically the same way as a disc in a manually operated valve. Its operation can be either linear, as in this globe valve where the disc moves up and down to regulate flow, or it can be rotary, as in this plug valve, where the disc rotates to open and close the valve. This is a typical control valve. The valve body contains the disc and the seat. The valve stem is attached to the disc so that the disc can be moved up and down to open and close the valve. The upper end of the valve stem is connected to an actuator. The actuator provides the power to move the valve stem in response to signals from the controller. Many different actuators can be used with control valves. Three general types are pneumatic, hydraulic, and electrical. The actuator on this control valve is a pneumatically operated diaphragm actuator. This type of actuator is commonly used in many process systems. An actuator is commonly operated by a corrective signal from a controller. However, in some cases, as in this pneumatic diaphragm actuator, the air pressure from the controller's signal alone is not enough to operate the actuator. To overcome the forces of friction in the actuator and the valve stem, and the fluid pressure against the valve disc, an actuator can be operated by a separate supply of higher pressure air. The higher air pressure is regulated by a valve positioner. If we move the positioner to one side, we can see that a mechanical linkage joins the valve stem to the positioner. This linkage, often called the feedback linkage, indicates the valve's position to the positioner. When the process variable in this system needs to be adjusted, the controller sends a pneumatic signal to the positioner. Then the positioner regulates the separate supply of higher pressure air to the actuator to move the valve to a new position. As the valve stem moves up or down, it moves the linkage. When the linkage indicates to the positioner that the valve is in the position called for by the controller, the actuator movement is stopped. In addition to valves, there are many other types of final control elements. Two of the most common are dampers and motors. Dampers, which are often called louvers, use a number of adjustable parallel vanes or blades to control the flow of air and other gases. In some systems, dampers have a pneumatic actuator with a positioner that controls the position of the vanes. During operation, when the positioner receives a signal from a controller, it supplies air pressure to the damper actuator. The actuator then opens or closes the vanes to position them according to the signal from the controller. Motors are also used in some process systems as final control elements. Motors provide the driving force to move, operate, or position components. For example, this variable speed motor is used to run a conveyor. Changing the electrical power supplied to the motor changes its speed, which slows down or speeds up the conveyor. While some motors are variable speed motors, many of the motors in a plant operate at only one speed. The output speed from a single speed motor can be controlled by connecting it to the process through a variable speed coupling. In this case, the coupling acts as the final control element. For example, this fan supplies air to a process system. It's connected to a motor through a coupling that can regulate the speed at which the fan blades rotate. When the supply of air from the fan needs to be changed, a signal is sent from the controller to an actuator connected to the coupling. The actuator adjusts the coupling to alter the speed of the fan, which changes the amount of air supplied to the system. In this topic, we saw how a control valve can be used as a final control element. We also looked at how pneumatic actuators and positioners are used to position valves. Then we examined some other components that can be used as final control elements. Now let's try some practice questions. The control mechanism in a control valve is the valve's disc. The disc works basically the same way as a disc in a manually operated valve. Its operation can be either linear, as in this globe valve where the disc moves up and down to regulate flow, or it can be rotary, as in this plug valve where the disc rotates to open and close the valve. If we move the positioner to one side, we can see that a mechanical linkage joins the valve stem to the positioner. This linkage, often called the feedback linkage, indicates the valve's position to the positioner. The output speed from a single speed motor can be controlled by connecting it to the process through a variable speed coupling. In this case, the coupling acts as the final control element.